Hey everyone. Okay, welcome to the
Awesome.
second stream of the day.
Hey everyone. Welcome to the Infrageometry working session. We left it last week on a pretty interesting note, and I'm really looking forward to just picking it up and trying to push and try to see some results emerge. So how about I give a very brief recap in 5 minutes to put everyone on the same page, and then we try to implement some stuff. So
Sounds good.
I'll bring a very familiar notebook to everyone in here. So let me just share. I'll just share the screen. Your faces so I can see them. I guess you're not seeing your faces. I'll see it in a second on YouTube. Like when I share my screen, Zoom is filtering your faces. Yes. Okay, fine.
Hmm.
Um, okay, so yeah, remember we are in the Infrageometry project. All we're trying to do is to recover something like differential geometry, but in a computational and finitary way. So we do that with hypergraph rewriting. So our placeholder for space or location information is a hypergraph, something that might look like that random small hypergraphs you have on the screen. We can generate these in many different
Carlos,
ways.
I think you have like a little bit shifted your screen. It's not visible, like half of it
Oh, really?
on
Oh,
YouTube.
I've got it now. Yeah, there we go. It
that was the problem before.
sometimes, yeah, it
Yeah, yeah.
sometimes zooms in. I can see the full screen now, and I've got us on the right-hand side.
Okay, so you should update. Yeah, that's on the streaming end, which is
Yeah.
yeah. Thanks, Dugan. Dugan also spotted on chat. Okay, I can see it live that it's good now. Okay, great. So yeah, so there are many ways in which we can generate such hypergraphs. That's not so much the point today. Today we want to really focus on deciding or maybe agreeing at least what are the good candidates for objects that we want to call functions, or we want to call vectors and things like that. So remember that the main sophistication here, the main piece of technology that we are bringing to the table that is more or less unique to the infrageometry approach is this idea of edges as places, where there is vertices that are considered as sort of your landmarks, where you can, or in this sort of outer space picture, these are the outposts where you can refuel, and there's a breathable atmosphere or whatnot, and the edges are the regions of space in between these space stations or outposts. So you can definitely traverse them with your spaceship, but you can't leave it on them. You can't just stay there. So, but they're nonetheless still places that you can go through, right? And so we have this idea of an edge place, and so we can get the places graph by just applying this edge place function to a given hypergraph, which is basically just going to create new vertices everywhere everywhere that there is an edge, and so we can use them to define certain things. And the most obvious thing is the tangent graph, which is the idea that from each vertex place you can navigate to the adjacent well, technically the incident edges, but in this new edge graph, edge place graph, the incident, so the adjacent vertices. So you have here some examples of tangent spaces, which are all the directed edges that come from one vertex place into the edge places. So you can put all of them together, and that's the analog of the tangent bundle. And you can think of assignments of such directed edges across all the hypergraph to think of that as a vector field. Last week we discussed about integral curves and so on. So those ideas should be quite quite established by now. I don't think there is a strong need to revise those. But the big question last week was, how do we think of functions? And Nick had a very nice suggestion, which I've now condensed as saying functions as multiplicity counts, effectively, which is I think is a very, very natural way to encode them, because indeed multiplicity counts are natural measures of hypergraphs. So it will be one of the things that we will be directly or indirectly making use of when working with hypergraphs. And so in the same way that you would make use of the topology of the hypergraph to define a path, you can make use of the multiplicity counts to define a function. So I really, you know, I'm totally sold on Nick's proposal for last week. Last week I was positive about it. This week I am totally sold. So I wanted to, so that was more or less where we left it. I think that being the proposal, it makes the definition obvious in some sense. Like if your hypergraph allows for multiplicities, then the counts are the functions. I think actually Uti might want to join us. So I'm just going to share the Zoom link if that's okay.
Yeah, I'll handle that. I'll send him a message on Discord quickly.
Okay. So basically what I was suggesting last time is that one way that we can try to see where this definition takes us is that we have a fair understanding, or you know, some initial promising understanding of paths, curves, tangent vectors, tangent bundle, and so on in this picture of hypergraphs as space. So if we now have a primitive definition of function, I would imagine that the definition of directional derivative should be very quickly definable, or at least very natural to encounter. So my candidate last week was to think about this particular rewrite rule that I'm calling the unary binary flow. Unary binary because it's a binary edge pushing a unary edge along, basically. So of course that's not all of the story. Multiplicities apply to all arities of edges, so it's not only for unary ones, but we can sort of just look at a very simplistic picture. We only have unary edges, and then we assume that there is some directed graph that represents the tangent graph, and then we can just look at that as sort of a primitive example of what a function can look like. And so my idea is that these rewrite rule could represent.
Hey, welcome. Thanks for joining us.
So
yeah, hi.
Hey there. So I was just doing a brief recap, and from last week, and so you remember Nick's suggestion to have functions as basically multiplicity counts, and I was saying that I was interested, positive on this idea last week, and this week I'm totally sold on it. So and I was suggesting that if we have a well understood notion of paths and tangent structure, which is basically what we recovered or recapped last week, I think that we should have a fairly easy time just defining what a directional derivative should mean, or what it means for a function to change along a vector field. So I think the key rewriting rule here, or the key probing mechanism for this kind of construction, is going to be this unary binary flow rewrite rule. So for that, we can make the simplification that our hypergraph basically only has binary edges that are undirected. So that means that you can always simplify as the hypergraph being just a graph, and your edge places just being vertex places, just for simplicity as a first analysis. And then you have only unary edges scattered across some graph, right? So then the question is, how do we make this rewrite rule work in a way that reflects some behavior that is characteristic of directional derivatives? So we might want to say things like, whatever quantity-like entity that comes from applying this rule gives for a given vector field, you want that to be additive when there's another vector field that can be added somehow, or or what is the behavior under composition? Will they behave like these weighted derivations that we saw in the discrete case, and these kinds of things. So that's kind of what I'm interested in. So I think we're gonna take the hypergraph packlet to a little bit of its limits in terms of the things that can be done quickly, in the sense that I wanted to generate some random hypergraphs with some specifications, but I think that was not working particularly well. But let's see. Because so I have this function here, the small hypergraph function, but that's just basically some, by hand hacking into the random hypergraph generation. So I wonder, I don't know if Nick, you want to maybe do it yourself, or just to have a because the idea here. So okay, what is the idea? So the idea is I have this rewrite rule. I think it'll be cool to just, I can just generate a hypergraph here. It's just not so complicated. No. So what I want to say is random hypergraph. So for example, I think say something like 7. And then I say, I think this is like something like this, right? What if I want 5 unary edges? I can do this, I think, right? Yep. You see, there's something off going on. I think I have to set some options to false or something. I can't remember. Do you remember here?
No. So what's happening here? Why the 3 vertices? Is it?
It's vertices and then edge specification per arity. Like if I said probably like I want 3 or 5, I don't know, say 3 binary ones, then it gives me. And I think if I say connected true, it might explode because there are not enough binary ones. Yeah. But if I just say 3, doesn't like it. Oh, no, it does. So yeah, it's currently, I can't remember what was with the just having, I think it's forcing connected. No, it was not forcing connected, but it was not including any vertices that are not used in edges or something like that.
No, that might, well, I don't know. I haven't touched this function. I can.
Yeah.
So I don't remember.
Yeah.
What is it?
Yeah. So basically, we would just need, actually, we might just want to generate.
Like it's not like very complicated. I think it just calls the resource function, whatever it's doing. And because it's based on the old hypergraphs without any vertex specification, it just generates whatever hypergraph without any vertex numbers, satisfies your edge constraints, and that's it.
Yeah.
Oh.
So
maybe there's some empty vertices should be added on top of that. It's not a big deal.
that's not what I want. It's red. Okay, that's better. Yeah, and it does this thing with the embedding that I think when it's pairwise, just defaults to some tree embedding instead of some electrical. spring or something. But anyway, yeah, but basically we can take, my point is we can take some hypergraph that looks like this as placeholder for a vector field, right? In principle, because it's going to say, if it's simple, it means that, you know, we're not running the danger of having multi-edges or loops or anything like that. So it's going to look like some region of the edge place hypergraph or edge place directed graph that we normally have. My point is that this kind of graph looks like this kind of graph. And you know, we're not separating anything into edge or vertex place, but that might not be so important. And then maybe it's easy to just add the unary vertices here manually, right? Like I just add some what it's a quick way to just random integer and you do range. Then you do what's this? Oh no, what do you mean? What do you mean is the output of this? So if this is some directed graph. Then I can do hyper graph. How would you do this, Nick, quickly? I'm just trying to add some random unary edges. It's not obvious that we
Well,
can.
there may be, I don't remember whether edge add function works.
Edge add, yeah, let's try.
Works, yes.
And then I specify the list or just the
Yeah, the list of edges, so a single edge. Yeah.
But it needs to be a different, another hypergraph object or just
No, just like no, just like list of a single list. Basically, just how you would write a naturally list of edges.
like that, right?
Yeah.
Yeah, that works. Okay, perfect. Then what I need is take length of edges at no, actually, isn't it edge count?
Yeah.
Yeah. Oh, not constant. Edge count of their graph. So this thing is how do I get this specifically? So random. Oops. Oh yeah, that's gonna add. Yeah, that's gonna add. Exactly. Yeah, that seems to work fine. I just need to make those lists. How can I do
map
that?
list over it. You just map list over it.
Just map list over it, right?
Sure.
Map. right? It will be the same as in this, like that, I guess. Yeah. But this should be the same. Okay, there you go. That wasn't too hard. Yeah. So I probably want this here, but anyway, I want the different here graph. Okay, so okay, that's a good one. Let's just keep that. I think that looks very good for what we want. So let me just take this somewhere else. This is have your faces here, make them a bit smaller. So take this to a calculus. Randoms that actually this can go. This is complete. All right. So if I want to say something like directional, so here's first the prototype. So in this kind of situation, we want to see how the unary binary flow rule applies to this thing. So what was again the code for this? I think multi-way system with, so this is what oh, what? Oh, it operated there anyway. That's fine. That's fair. Just gives you. Was it rules first?
Yeah.
Then, yeah, photograph and then the number of steps, right? So let's do maybe 3 steps. Oops. What's the problem? Unknown box name.
I don't think there's a number of steps in there. Just an object.
But how do we know how long it's going to go?
No, then you ask some properties. Like if you want a graph that applies 3 steps, then you ask for a graph with 3 steps.
How was that again?
Well, it's like a property. You ask for a graph. Try this one first. No, don't write anything else.
Sure.
And then you ask for a graph of this object.
Oh, I see. Like states graph, something.
Yeah. Just graph, evolution graph, causal graph.
Yes.
You may like increase the vertex size. Maybe you'll see those.
So this I applied to the whole thing?
What do you mean?
How do I change the where? Is it
Yeah. Just here. Just add an option of vertex size.
in here?
Yes. No, without quotes. It's like for a graph.
I want to do it like number?
Yeah, a number.
Yeah, it seems like more like right. Yeah. I think I need to update the rule. So I'm gonna, so currently the target hypergraph has only this, but I'm gonna preserve the edge. Yeah, I'm going to preserve the edge just in case. So yeah. So I'm not sure why is it showing only one step. Can I give it
Well, you ask, yeah, give it a number.
Ah, right. Yeah. Okay. It's not particularly useful. This is interesting. So I wonder if I run it for X. I guess it would. This is interesting. Like at some point, yeah, that's interesting. So anyway, I think this is enough to illustrate what I was trying to say here, which was this is a sort of a prototype of what the tangent graph looks like, together with some unary edge information, which is something I would like to call a vertex function. So, intuitively we were assigning numerical values to vertices, and this is just the fact that because you might have unary edges sitting on vertices, then the multiplicity of those will just give you those functions. And so the idea of a directional derivative, remember, is this idea that your vector field or your curve defines a local flow, and you can compute the rate of change of a given function alongside a particular flow. So a particular flow here is represented by a particular directed graph on a set of vertices, and the function is represented by this particular distribution of unary edges. And the idea of flow is represented by this rewrite rule, where whenever you have a unary edge here on the tail of a directed edge, it gets rewritten to pushing the unary edge to the head of the directed edge. So sure enough, if we begin as our initial state, we have this particular hypergraph. This single rewrite rule gives this multi-way system where things begin like that, and then you apply somewhere. I guess we're applying it in 1, right? 1 is flowing onto 2. You see it's more shaded. It's there's weight 2 over there. Here it applies, I guess, on 3, and it's actually, oh yeah. So actually, yes. So that's right. You only have 2. It's a good illustration. So you only have 2 matches of the rule because you only have the arrows are pushing in the directions. If I make it bigger, I don't think the diagram is bigger, right? Or is it? I don't know if the actual vertices. It is a little bit bigger. Okay, so I guess I can make my screen a bit bigger. Yeah, okay, that's better. Yeah, so as you can see here, the unary edge on 1 has a tail of this directed edge, the 1-2 directed edge, and again, this unary edge on 3 has the tail of the 3-5 directed edge. And that's why we have two matches. So we have two rule applications here. Note that the unary edge on 2 and 4, they are at the head of the directed edge, so that's why there's no rule application there. So in this path, we moved the sort of package from 1 to 2, and then in this one we moved the package from 3 to 5, and then but of course independently. So now if we move the package from 1 to 2, having moved the one from 1 to 5, so 3 to 5 again, then we are left with this one, right? And you know, then this package can be moved again, and I think this is now moving it to 4, and it's pushing it up there, so that's where we end up here, and so on, right? So the packages are being pushed, and I imagine at some point the packages just don't move anymore, right? So you reach some sinks. And does it look, these don't look like final. It's interesting because for some reason these don't look like final diagrams, but they are.
Well, maybe one more step.
Maybe.
Actually, multiple.
I think it's 5. This is 1. It's 1, 1, 2, 3, 4, 5. Yeah. It happens. See. Let me zoom out for a little. Ooh. For some reason, these two are not identified, but yeah, these are not identified, but they are clearly isomorphic hypergraphs.
They're
But
not
anyway.
I don't think they're identified by default.
Ah, okay. All right, then I think this is now showing the pattern. It's a little bit sort of scrambled here in the middle, but you get the point. So you begin with this distribution. The rewrite rule basically pushes all the unary edges alongside the directed edges, and your terminal states here all are sort of inert states, or so all the packages are always at heads of directed edges but not tails. And yeah, so that's basically a rewrite implementation of the notion of a function flow. Now the question here is, I wanted to bring up this to the screen so everyone can sort of comment and have an intuitive picture in mind. What do you think are ways in which we can come up with some computational construction here to try to extract something like properties of directional derivatives, which should be something like additivity. I mean, additivity should not be that difficult, I guess, because multiplicities are just naturally additive, so I'm not too worried about additivity, right? But the crucial one, I think, is about so we have a bit of a problem to think about what the notion of multiplication of functions, right? Because directional derivatives are algebraically identified by the fact that they act as derivations on functions. So here it will be interesting to think about how that can be even expressed. But for that, we even need a notion of what it means to multiply two functions to begin with, which is not obvious at all to me. that sounds like it should be incorporated with a rewrite rule as well. Because function multiplication is an algebraic operation. And if we are saying that our functions are just multiplicity counts, then that sounds to me like we should be writing down some rule that does multiplication, but it's really unclear to me.
This is part of the sum rule, right? You're wanting to get like product, Leibniz and sum and chain and all these things.
That's right.
So it's a scalar by the function, something like that. Just to make sure I'm following.
Yes.
Correct?
So right now functions, sorry about this. Right now functions, we are trying to think of them as simply multiplicity counts. So they give us exactly what we were intuitively defining them to be initially, which were assignments of numerical assignments to vertices or edges, and now it's that, but the numerical assignment we are going to take as arising from the multiplicity counts of some edges, so that we can actually forget about the fact that we will count the edges at all and just operate with hypergraph information for rewriting. So
labels, right? So instead of multiplicity, you replace with labels. Right?
Yeah. So labels we might want to use to
unless it's cheating. But then the other thing is like, is there some natural way, just as you do with like lambda calculus, that you can define hyper operations? Is there some way that we can just sort of build everything from this, so you get addition, multiplication, exponentiation, tetra, you get everything kind of for free? Is there some way with rewrite rules that we can achieve that, or are we lacking some sort of higher order?
Okay, so let's give some reality checks. So for example, we can clearly recover additivity, so the addition of functions, right?
Okay.
This is easy simply by what we have defined as addition of hypergraphs, right? So our current definition of hypergraph addition exactly recovers function addition.
And does it translate the sort of natural sort of repeated addition is multiplication? Does that, or is that?
Well, that's not even, we don't even have that in normal geometry, right? In normal geometry, you just assume that your field of numbers, your scalars, already have the structure of a ring or semi-ring or a field, and then you inherit your functions to carry that structure pointwise, by pointwise construction. But here it's not so obvious. So
that's why I'm thinking more functionally.
Yeah.
Wait, Carlos, what do you I'm not familiar. Like, what is hypergraph addition? Like, is it like
that's just disjoint union of its sets basically. But yeah.
Oh,
so
okay.
Yeah. So it's no, not disjoint union, sorry, it's additive union. So maybe I can just say 2 words very quickly about that. So additive union of hypergraphs means that you're going to take the union of the sets, right? And of the vertex sets, right? So all the vertices, you do the additive union of that, just the union.
Okay.
And then you're gonna take your 2 edge sets
And disjoin them.
and then you're doing a union over the union, right? So it's so you're basically, if you have it's additive union because it's basically just union. So theoretically you have simple hypergraphs, but if you want to keep track of multiplicities, then you might want, you might have some edges from the first hypergraph that also appear in the second hypergraph, and you want that when you add them, you keep track of both. So you keep track of multiplicities that way. So it's basically multi-set union.
Yeah.
Also, it's like you have V1, V2, and then another hypergraph, you have V1, V2. And if you have an edge, V1 goes to V2 in both of them. Then in the new graph, you'll have 2 edges between V1 and V2.
That's right. So you do
Okay.
you do set theoretic union for vertex sets,
Yeah.
but you do multi-set union for edge sets.
Okay. Yeah, that works.
That's what hypergraph addition is, and I think we can illustrate that pretty quickly. I think hypergraph. I mean, hyper A. Let me just draw a quick. No. Crash the whole thing. You see, Nick, my frustration. Just draw a simple hypergraph and just crashes the whole thing. Okay. So I will not draw a hypergraph.
Oh, you're lucky that it's not doesn't crash the whole
The whole
process.
computer. Yeah. At least it doesn't kill the whole computer. Yeah. And not even the notebook.
That was my experience recently using some different dynamics, trying to do some more dynamics again.
Oh no. Okay. Yeah. Dynamics, the bane of our existence.
What happens when you push the boundaries of mathematics?
I wish this was the cause. Now you do the usual thing when I have to abort the first run and then do the second run. But yeah, basically addition, I'm just hoping to just off the shelf be able to add two hypergraphs together and it will be obvious. But I can do it here, just not to write something here in the end. Yeah, so I'll do it here just for maybe too small for the screen. So, oh, I can just take some of these actually. Yeah, that's much easier. So, for example, if I take this one and I show the I show the vertex labels. So say vertex thematic. Okay. And I do the same thing with whatever, this one, for example. Right? No, I didn't want to choose that one. Let me just choose this one. No, that's this. I'll just choose this one. Right. So you can see, actually, that's exactly what I wanted. I'm sorry. So you can see there's a vertex there that's new. It has some sort of code name. But you can see that there's some shared vertices, 1, 2, 5, 4, 3, and then there's an extra one, right? So I should be able to call this hype A, and this can be hype B. And I can now do hype A plus hype B. Yeah, and that works really well. So that's exactly what a hypergraph addition is like. It's basically additive union, but it's additive union of the edge sets. So if you apply this to unary edges, we have vertex functions or whatever. That's exactly addition of functions, right? Because that is exactly what we have. What's interesting here is that that's not a rewrite. I mean, we're not implementing it with rewriting itself.
I was going to ask, yeah, is this something extraneous to the the thing, just some analysis that you're doing, or some construction that you're trying to build, or is it something that you could in principle implement within a rewrite system?
I mean, there's this ambiguity. Well, not ambiguity, but I guess there's always the option, and there's something that I have had in the back of my mind since I started thinking about rewriting for any kinds of applications, algebraic or infrageometric or otherwise, that you can always.
You could in principle.
So this construction, this is what you could call something like an object-wise construction. I mean, you have some horizontal construction where you have hypergraphs as static, as independent objects, and you can operate them with some kind of algebra. And something that I've always thought about is that you can always see those as very sophisticated rewrite rules, right? Where you're allowing, for example, potentially disconnected hypergraphs to be combined. Like the information of these two, the problem is that the information of what Plas does here, in some sense, is basically saying consider these two at the same time, right? So for those of you who weren't in the previous live stream, we just introduced the basics of hypergraphs, and I gave this picture of vertices being like memory slots or memory locations. And so if you say that your hypergraph lives on the memory locations 1, 2, 5, 3, 4, exactly with this relational data on it, and your other hypergraph lives on these with this extra memory location here, then the point is that if you express these two simultaneously and you pay attention to both collections of relational data simultaneously, that's what the addition is doing, basically, right? It's just saying consider both at the same time. But the fact that they were separate in the first place was already some kind of choice that you made. It's like, I'm going to look at that relational information on those vertices, and I'm looking at this other relational information on those vertices. So addition here is really only saying, take all that information together, right?
Collapse those parallel universes into just one little universe, I guess.
Pretty much, yeah.
Maybe not so literally, but
yeah. But conceptually, yes.
So this is interesting.
But anyway, the point is, addition here works quite well. And intuitively, you can think that whenever you have anything that the rewriting will do, so
it's like when you did that emulation thing, like you can sort of fine grain a computational process as much as you like, and if you have universal rules, you could kind of do anything. But it begs the question: it's like, what's the point? Like, what are we? Why would you want to? Why would you want to sort of mechanically implement this process as a kind of rewrite system rather than using it as a tool to build some formalism, like you're doing?
Yeah, but let me make a very complete statement here that I think will make sense to Uti's question. I think might guide a little bit our discussion. So, okay, note how by construction of our rewrite rule, right? And do keep me in check. If I say something stupid, please correct me. By definition of our rewrite rule here, if I give this this kind of diagram, oh wait, this has a loop over here. So yeah, so I was going to say something that is only valid for a DAG. So imagine that we have a DAG, just for sake of argument, right? I just wanted to make a point. Imagine that were a DAG. So that might be why it's not terminating, I guess.
It's got cycles in there for sure. So
exactly, yeah. I don't know, yeah, but wait, what is that graph? That's not the same graph, is it? Oh no, it is. It is the same graph, just down here. Okay. That's funny. Yeah, anyway. So yeah, you shouldn't terminate because that thing just loops around, just cycles all the time. Anyway, so imagine that this is a DAG. And so that when you give a distribution of unary edges and you flow with this rewrite rule, that always reaches one single final state, right? So it's just the confluence is trivially confluent because all you do is just flow and until you can't flow, right? So you agree that if you begin with a random distribution of, any distribution of unary edges on a DAG, and then you apply this rewrite rule, you eventually get one final graph with the unary edges all accumulated in the heads, right? In the terminal points of the DAG.
Yep.
You agree?
Yeah.
Okay. So the additivity property of directional derivatives, or whatever this is, could be seen as, if you begin with two hypergraphs, so two such distributions of unary edges, and you apply both to both the rewrite process, the relation of the values in the end is exactly additive, right? Should be, right?
That was for after you dealt with the section.
Say it again, Richard. Couldn't hear.
Oh, were you just thinking, or had you read what I posted? I just wanted to make sure that I didn't interrupt you. That's all.
No. I was just thinking, but like,
Cool.
I think if the system is always terminating, I guess the problem is it's not really, it's terminating, but it's not confluent, I think, right? Because even if it's a DAG, you might have branching points, in which case you have more than one terminal.
We have a couple of questions. I don't know if it'll help to take some questions and then think back at this.
Oh, yeah.
But
So-
I don't want to interrupt your stream of thought.
Yeah, no. I have the questions in front of me. So, Brady is asking about multiplicity. So multiplicity is just the count. So we are really thinking about finite sets of edges. So things that you're seeing on the screen are faithful representations of the kind of objects that we're thinking about. And multiplicities are just the counts of such things. So, the multiplicity on the vertices here will be 0, 1, 1, 0, 1, 0, 1, right? And if there's some extra unary edges there, then you would have higher counts, right? And yeah, Eric just gave a very good answer to that. So someone, thanks a lot for that.
Richard had a question there about subtraction.
That was
Yeah.
really for after.
Okay.
When we come back to the thing below, it was for that.
Yeah. We can think about that. So wait. So maybe the argument still makes sense. I was just trying to make a point that I thought was more or less uncontroversial and intuitive, but maybe it's not so straightforward. But so the intuitive picture is, if you have the same structure of a graph, of a directed graph, let's say acyclic, just for the sake of argument. If you have a distribution of unary edges, which is like some mass that can flow on that graph, if you flow it all the way into its last consequences, you push it all to the terminal vertices, that might not be a single final state, because there might be bifurcation points or whatever, but you might have some sets of terminal states, right? And my point is, if you have two distributions of unary edges, so two distributions of masses, the relation, so the only difference between final states is the total mass of each terminal vertex, right? I'm pretty sure, right, that if it's a DAG, if it's an acyclic graph, that you can argue.
Is it some kind of conservation argument that some?
Yeah, exactly. I mean, it's basically conservation of mass, right? If you begin with a total mass A and total mass B, and you flow all the way to your terminal vertices, then if you keep track of all the possibilities of distributions of mass, you should have additivity, some kind of natural additivity property, because basically just by conservation of edges, that your rewrite rule is not destroying edges, right?
Nice.
Something like that. I'm just making again, this is not a technical statement, just intuitively kind of trying to, and then you could, you could imagine that, you have your hypergraph, you apply all the rewrites, so you get this tree with terminal states, which all have the same structure, same underlying directed graph structure, but have different distributions of unary edges or mass.
But it's like space-time separation or something between the two. Analogously, again, not a literal statement, but yeah.
No, it's something like that. But the whole point is that you can, my point is because you can perform hypergraph addition at any stage of the process, right? So you can perform hypergraph addition when you have two initial states of unary edge distributions. So you can have actually one single initial state, and you can evolve that, and you get to some final states from the A plus B initial hypergraph. Or you can evolve A, evolve B, and get to some final states. And then you can perform on the final states, because they are all going to be, there's a one-to-one correspondence to what are the final states, because they are all the same underlying directed graph. My point is that there will be something like, find the counts of unary edges for some terminal state of the A plus B evolution, and then do the same thing for A, do the same thing for B, and then add them together. And there should be some kind of commutative diagram there. Something should be conserved. That's more or less the picture.
Something equals 0.
Yeah, or something plus something equals the other thing plus the other thing.
Yeah.
So, and Nick, do you follow what I'm trying to say here, more or less?
No, not entirely. It's like, especially like this constraint to just a directed case. And what is the big picture anyway?
Yeah. Well,
can we
you mean
summarize?
directed or acyclic? You mean directed, or you mean?
Yeah, the restriction to the DAG.
Oh yeah, DAG. The important part is that it's acyclic. But the point of being acyclic is that you have terminal states of your rewrite system. So otherwise, it's not obvious where to look. But even if you didn't have terminal states, you could find some construction, some algorithm that tells you which states to look at, right? And the point is, perhaps the point I'm trying to make is more intuitive than just thinking about the full evolutions. But the fact that your rewrite rule preserves the number of unary edges, right? And addition of hypergraph addition conserves the number of edges. That's what it does, right? It's just basically keeping exactly the count in the process of adding, of constructing a new hypergraph. So the question was, so the idea is maybe additivity is obvious in this case, because if your rewrite rule doesn't destroy edges, then you are going to be additive, right? Maybe it is as simple as that, but I don't know. I mean, let me put it another way. If your rewrite rule does destroy edges, then it's clearly not additive, right?
What if it destroys and creates?
Yeah, what if it's in aggregate additive? Yeah.
That's the complex part. Yeah.
That's why you need to evolve it to the final version, because in finality, is it additive or not?
That was my point.
Okay.
My point was that you have a complex evolution. You don't know what happened, but something might get to a point where you have commensurate hypergraphs, that they are the simple versions of those hypergraphs are isomorphic. So again, remember that we call those skeletons or something. When I say skeleton, I mean that you collapse the multiplicities into the simple hypergraph that is sort of in the background. So isomorphic skeletal hypergraphs will have different edge counts. So the only difference will be the edge counts. And the point I'm trying to make is that you might explain the relations between the edge counts by some direct additivity property. But again, trying to get literal additivity might be too much to ask for the general case, because we are breaking algebra by considering rewriting and being sort of sort of state-wise and being discrete and being computational and so on.
Is
So,
there,
so
is
in the end, what here?
Yeah.
Are we trying to define some kind of linear rule that so that it's additive?
I don't know. That's the problem. The problem is what I'm trying to do, or I'm trying to think through, is what would be a check or a pattern or some kind of phenomenon that we can observe at the rewriting level and simply at the measurement of hypergraph metrics level that we can say, that's analogous to additivity of directional derivatives or additivity, just additivity of functions. I mean, additivity of functions, I think we are all agreeing that it's captured by the process of hypergraph addition because it's kind of an intrinsic construction. So even thinking about what function multiplication means in our context is already something interesting and difficult because not obvious to me what that is.
Yeah, because you need things like annihilation, right?
For the subtraction.
Yeah.
So
just
do we consider like opposite edges annihilate together? Like as an alternative addition instead of just taking the joint union of edges. We also annihilate opposite edges if they have a direction assigned to them.
Considering assigned edges or something, right?
Well, for example, in our case, we have arbitrary symmetry assigned to hyperedge. Right? Symmetry is like some kind of group element, so it's had an inverse. So as soon as we add two edges together that has the inverse symmetry, then we just annihilate those edges.
I don't think that really works in the sense that would not be hypergraph addition. So that would be some kind
as
of
I said, it's like an alternative.
Yeah. No, but
notion
that would be like providing some kind of signed structure. But I think you can do that even without any reference to the order of the edge, in the sense that, I mean, you want to.
I guess I was just in search of all the usual like identity inverse, multiplicative identity, multiplicative inverse.
Yeah. So let me quickly address the questions here in chat because they are easy. So Dugan is asking, so what's being considered is a function from the set of edges to n. Effectively, yes. Multiplicities, that's effectively what we are thinking about right now. So that's where this term, the skeletal hypergraph, comes in. So you would have a function from the skeletal hypergraph to n, which is a simple connected hypergraph, or let's just say simple. It's a simple hypergraph, and it's evaluated to n. And then, Eric very correctly pointed out that that's the case. And Eric said, although I think we are just thinking about vertex functions from between right now. Yes, so we are, for simplicity, just considering unary edges. So we are using this sort of cartoon of a tangent graph where we've sort of forgotten exactly how we got here. And we just say, okay, let's have a directed graph, which is our placeholder for what would be the actual tangent graph of a hypergraph, which is a bipartite directed graph, and then we have unary edges, which are the only undirected edge information that we're going to consider as which is essentially like saying that we have some vertex valued functions, so some integer valued functions on vertices. That's basically what we have.
Wait, product of functions, can't we just isn't it like a product of graphs or something?
That's very likely the case. I was thinking about, but the problem is that we might want to think, like the problem is that function multiplication seems to be function multiplication is pointwise. Most graph products involve some vertex-wise products that take either Cartesian product or something like that.
And which do you choose? Like what and why?
Yeah.
Like over here, I think what we're doing, we're just like doing like the set theoretic, like in the case of addition, it's just a set theoretic push out, right? And in the case of addition, which is the disjoint union, and in the case of, so like here we're just treating the vertices as not part of the graph. Like the graph product involves the product of the vertices and the edges, and the graph push out involves the disjoint union of the vertices and the edges. So over here we're kind of keeping the vertices constant, and we're just doing like set theoretic constructions on the edges.
Well, we can certainly be making these set theoretic constructions on the edges themselves, which
Yeah.
it's equivalent to basically saying we just have weighted edges by your favorite algebraic object.
Yeah.
And call it a day.
Yeah.
I'm not saying that's not the way to go, but I was hoping to maybe get something out of the simple case, simple meaning technically simple, where you just have unary edges, you just have a rewrite rule, and your rewrite rule doesn't need to know about any of the algebra, because the rewrite rule might need to incorporate we'll have to incorporate the algebra explicitly, right? It's like, if you imagine this rewrite rule, but you weight the directed edge by some kind of flow rate, then this is the sort of extreme case where flow rate is 1, mass charge is 1 in one end and 0 on the other, and this result is flow rate 1, so you send 1 unit of mass and you deplete down to 0 mass in that point. But you might weight it and just have a more realistic, so to speak, implementation of flows and things like that. But the whole point here is that in infrageometry, we kind of really want to avoid introducing algebraic structures by hand, that would be just basically just tagging along some kind of external, like you would have to do that arithmetic somewhere, right? Computationally, you would have to have your, calculator that does all that arithmetic for you. And the hope here was to get something that does work just by rewriting hypergraphs, nothing else. Right.
I see. I mean, hypergraph addition is not really rewriting, right? I mean,
what is? Sorry?
Like the addition of hypergraphs?
Addition of hypergraphs is not rewrite. I mean, in some technical sense, you can define it as rewriting in a very kind of.
That's the point I was making about once you have universality, whatever, you can just do it.
Yeah. By the way, so Dugan is asking, so function counting edge multiplicity yields the additive relationship FA plus FB equals FA plus B. Yeah, that's basically right. So that additivity property is clear for the case of just addition of hypergraphs, just the additive union of hypergraphs as multisets of hyperedges. Additivity is clear there. Like we have good all additivity at that level, but the idea, if you take multiplicity counts as functions that take your edge set into N or into Z or whatever count you're doing, here the expectation would be something like, if you give me 2 hypergraphs, can you deduce some kind of additivity property just by performing the rewrite rules on them and just by measuring the edge counts at different stages? I think that's basically, maybe I'm answering my question just by saying it in some sense, because it might be that your hypergraphs have a lot of topology information in them, so they have a lot of things are flying around when things are being rewritten and changing and whatnot. But the moment that you say, I only care about counts, right, and where the counts are in some sense, then your rewrite system goes from a hypergraph rewrite system to a integer, for example, rewrite system. where you might have for simplicity in these examples, you have a list of vertices, right? A tuple that all these vertices are labeled, and then you have a list of numbers, which is the edge count on each vertex, the unary edge count on each vertex. So then every step of your rewrite basically changes that list of numbers. So it becomes a rewrite system of, or at least a multi-way. I'm not saying a rewrite necessarily, but at least a multi-way system of lists of numbers, right? Basically of tuples of numbers. So it might be that additivity is a property of that particular multi-way system, which is, it no longer has topological information because it just has a list of vertices and only numbers on them. You don't know anything about you can no longer see the topology of the hypergraph. You can only see sort of a histogram of counts. But if these histograms of counts come from a rewriting system that cares about the topology, as it does here, some property of the numerical rewrite system or the numerical multi-way system might, capture or express somehow the idea that things are additive or things are, multiplicative or Leibniz or things like that. I think that's maybe the answer to what I was asking. Exactly what to look for in that rewrite system is not entirely obvious to me.
For the creative juices, I can throw some random ideas out there, unless you need to concentrate in silence.
Silence from time to time is good, but do go ahead.
Okay, so I was just thinking of this maybe from a different angle, like dependent types, where if you have because multiplicity, from what I understand, is like, let's say you have unary edges and there's 5 unary edges on your hypergraph. So then you're saying that there's 5 of them, but they're all of the same type. And then a binary edge is like a different type, but it depends on the first type. A binary edge contains unary edges, and so you can go up the order, like binary, unary, ternary, whatever.
Wait. Why does it depend on the unaries?
Because a unary edge can exist inside of a binary edge, or no?
Not really.
No,
because
in this system with your little mass moving along the edge, it kind of they're always in a neighborhood of each other, right?
Yeah, we are simplifying to only consider unary edges, but even if we were to consider binary ones and higher arity ones, they don't interact. That's why I think it's fair if they don't interact unless we make them interact by a rewrite. Okay. So in this particular case, they are interacting because our rewrite rule is exactly, unary edge moves along a directed binary edge, right?
So by move along, you mean it's been rewritten to do that? Something like that. Yeah, there exists a rewriting rule that transforms the graph as follows. Yeah.
Exactly. So unless this is an interaction between unary and binary. That's why I call it unary binary flow rule. But in general, unless you specify the interaction, unary edges, binary edges, they all exist in parallel. In fact, that's another way to think about the hypergraph addition, right? So you can take any hypergraph, you can take what I call its gradation, which is basically factorize it in summands of uniform hypergraphs. So you can take all the unary edges, and that's a hypergraph. You can take all the binary edges, that's a hypergraph. You can take all the ternary edges, that's a hypergraph. And your original hypergraph equals the sum of all those together, right? With sum being this operation that we have very clearly defined here, and we have computationally implemented and everything.
But how do you know where to connect them if that's the case? If you're separating them out, which vertices are you connecting it along?
Well, we're assuming that the vertices carry their names, and those are being kept.
Okay.
So you're not connecting anything. You're just throwing more edges on top of the same vertex set. Again, this idea that vertices are the memory locations and edges are just information that comes on top, that sort of floats on top, and you can stack as many as you want to have multi-hypergraphs. So that's why you don't really, unless the only way that these things interact is via rewrite rules. But addition here is this kind of observer, kind of user-based operation, which mostly just refers to what you're paying attention to at a given moment, right? It's like if I pay attention to A, this is the hypergraph. I pay attention to B, this is the hypergraph. But when I want to pay attention to both A and B, I have this particular operation that computationally just puts everything together. But
So
if you can't put everything
no rewriting is taking place during these types of operations. It's not. So an operation is different to a rewrite application.
yeah, so as I said, you can define this with rewriting,
Yeah, it depends how you want to do it. Yeah.
but it becomes this kind of technical gymnastics of like, okay, give me your hypergraph, give me your A, give me your hypergraph B. I'm going to rewrite all the labels in B to be different. So I'm going to give different names to all the vertices, and now I'm going to check for isomorphism here. So I'm going to do rewrites exactly. So you can build this algorithm where you're essentially collapsing matching edges by rewriting maybe a higher arity edge between all of them, and then you collapse it and you delete it. It can be done, but it's completely artificial. It's very this is obviously a very natural operation. So yeah, let's keep the questions for a bit later from the chat, because yeah, I would like to get some clarity on this first.
Richard posed a question. I don't know if that helps.
Yeah.
Richard?
Well, I don't know if it's useful really. Just following the journey from state to skeleton, it's like, because that's a kind of prerequisite before this operation, right? Is that correct? If I understood, I'm also trying to catch up because I missed a couple of.
No, sure. Yeah, well, yeah. The summary of what we're trying to do is, we seem to have a strong intuition that paths and flows on a hypergraph are going to be represented by a directed graph. Nick's suggestion seems very attractive, in which functions are just encoded by taking multiplicity counts. So it's kind of, when you reduce what it means to take a function in this sense is it means that you become blind to the topology of your hypergraph, and all you see is numbers, right? You just get numbers out of it. And to simplify, we are making that coincide with just unary edges. So you literally don't see any topology because you just see numbers distributed.
Yeah, that's your readout. That's like the property that you're observing. The rest is like your background space. Well,
exactly.
Like that. Yeah.
Exactly. So the question, perhaps more concretely, I can phrase now. The question is, if you have a hypergraph, if you have a situation like this, where the directed graph stands for some tangent graph to some place hypergraph from infrageometry context, but for now, just a directed graph. And you have some unary distribution of edges there. This particular rewrite system, rewrite rule, seems very intuitive to be encoding what normally one thinks of in directional derivatives, which is flow, right? Basically, the fact that you can move things along. So the idea is, the moment you consider the rewrite rule in this kind of hypergraph, you have a multi-way system. So for example, you can observe here that you have some multi-way system, right? The thing just starts to evolve. It has some dynamics. And the question is, the fact that you're taking multiplicities means that you're extracting from each state in this dynamics, right? You're extracting numerical information. And that information is precisely of the form a 7-tuple of numbers in this particular example, right?
Yeah.
So 1 to 7, each of these numbers will have sort of a histogram on them, 0, 3, 2, 5, 2, whatever, right? It will have some distribution of values. And so the question here is that, can we find some kind of property of the numerical? So this is a hypergraph multiway. The literal rewriting system becomes a hypergraph multiway, which is this DAG, right? This particular rewrite system. But if you look at the multiplicities, it is no longer a multi-way system of hypergraphs. It's just a multi-way system of 7 tuples of numbers.
Yeah, yeah. I think I was with you to this point, and then the
So we're trying to probe somehow. I was using the possible example of additivity of you do 2 things, then the same thing, but for the additive of the 2 things, but it could be anything. Like it doesn't really. I think it is more clear in my mind now that
that's why my question has gone to like other, like this is presumably some kind of binary, you could think of it scalar field, but then you've got properties like divergence and curl, and so there's got to be some way of fitting these into the picture. Eventually,
we
kind of jumping the gun.
No, that's definitely relevant. I mean, we anticipate. I don't know how much we can take direct inspiration from actual differential geometry. That's part of the game here. But I mean, I anticipate the curl and div, all these things should show up. But obviously, we need more structure.
All sorts of other things that you can do. I mean, this might be obvious. Like I said, I've missed a few of these things. There's be like a whole set of operations that are very difficult to define in sort of traditional calculus.
Well, that's the thing that I think this is I mean, just for in case the viewers are wondering, like this is exactly how research looks like, where you have no idea what you have to do. I mean, and part of the challenge here is that we really are going into uncharted territory here. And I mean, we're trying to work based on analogy and trying to call back to familiar situations, like, you do A plus B, and that's the same thing as first doing A and then B, and then doing the result plus the result would be whatever. I mean, that's just trying to call back to familiar situations and to things that are familiar to mathematicians and have appeared in many different settings. But it might well be, so I think it was important for me to formulate the problem in such a fundamental way here. Fundamental as in, we have a rewrite system, we have a hypergraph, we infuse dynamics into it with a rewrite rule. We are agreeing that this seems like a very reasonable sets of definitions for infrageometric analogs of vector fields, functions, and flows, and things like that. And then the question is, okay, if we are thinking of our functions as just multiplicity counts, then the problem of identifying whether this shows some kind of property is to relate the properties of the entire rewrite system of the hypergraph with the rewrite rule that we've presented to the rewrite system or multi-way graph of simply the number distributions, if you can somehow relate it to. Yeah,
how do PDEs and ODEs come into the picture here?
I mean, we are trying to basically define a derivative. That's where
we're sure. That's why I'm skipping ahead to that.
Yeah. So we're basically trying to define a derivative, and to me, this picture here might be the fundamental infra derivative or something like that. And the question is whether we can piece together by somehow doing nice analysis on the multi-way systems that derive from applying this rule to some arbitrary situation, whether we can derive properties that would tell us that is indeed a derivative. You found something that does indeed work as a derivative.
UT has a question, and I also have a question on that, what you just said now.
Yeah, please, Udi. Question or comment or
Yeah,
anything.
I was asking that, so you have a given vector field and the directional derivative is like a function from each point to
Yeah.
like the natural numbers, right? So over here, like I am struggling to understand how does I understand why the flow operation makes sense because you're like moving some values from one part of the graph to the other. How does that give rise to like a new function?
Well, I mean, quite simply, if we are assuming that our function is a multiplicity count,
Yeah.
right? Then that is well defined for every state of the rewrite system, right? So that's why I'm calling it an infraderivative, because technically speaking, you could think that each of these states they all have functions with different values. Well, maybe not different, but generally different, right? So each single application of the rule, so let me put it this way. There is one thing that we call the one-pass rewrite, which is, or I call the one-pass rewrite. I don't know if it's a good name, but basically it means that you find all the possible matches of your rule, and then you output whatever you output the result of all those on the same set simultaneously,
Right.
Yeah. Without going in this sort of multi-way. You just do one single application, one pass at all the matches, right?
Yeah.
So if you did that to this rewrite rule,
Yeah.
then you would get exactly sort of a finite step flow of your function, right? If you
you would get the directional derivative.
Not the directional derivative, you would get the flow of
the dynamical evolution, right? You would get
the dynamical
system
evolution.
evolve.
That's right.
Yeah.
You would get this idea that you're pushing values along your graph.
Right. Yeah, I understand. How is that?
Yeah.
So like if you're viewing the multiplicity thing, then the directional derivative should give you the directional derivative function should basically be another graph.
Yes, and that's the graph I'm saying, that you take, in here. I mean, it's easy to visualize in this one, right? You take this graph, right? So so this one, this edge here is not going to get pushed anywhere because it's already in a head, but this one is in the tail of this edge. So you push it along.
Yeah.
So it gets here, then you match again, and you say here, okay, this is already in a head. This is in only this tail, and you push it along, right?
Yeah.
So the end result of applying the one-step flow is this graph, but with a unary edge there and a unary edge here, and a unary edge there.
Yeah.
So the new function is the multiplicity count of that graph.
Oh, okay.
Right. So actually now that I'm thinking about it, so earlier I said something, maybe when I was talking about the DAG, I said, oh, there might be bifurcations because of, the DAG having bifurcations. Interestingly, vector fields don't have bifurcations by definition, right? So we don't have that problem. We do have the problem of cycles, that you might still have loops, but that should be fine. In some sense, I don't think that should be a problem. I was more worried about the indeterminacy of branching points, because you don't know how to flow your packets. But basically, by definition of vectors, the application of this rewrite rule does determine either a terminating, either a confluent system or a system that is confluent on a cycle of states, in some sense, right? You end up just you can imagine, right? Like you have some cycle of vertices where your mass is flowing and it's just kept there like an attractor in some sense, right? So all your, because everything is finite, you might have a long cycle, but you will have a finite cycle there. So anyway, just as a comment from the previous,
kind of like a singularity almost, maybe.
Yeah, but just like I mean, everything looks like a singularity in the sense that everything gets pushed into a final place. So it might be, that place might be a an actual vertex, or it might be some cycle.
Like a vortex versus a like a cycle is not necessarily a singularity because it might not be attracting everything to it. It might just be spinning.
That's right.
But I guess
So once you're in it,
like a vortex. Yeah.
okay, quick question then. So remember when we were talking about this bipartite version of the hypergraph? I thought in order for that to make sense in terms of what you're trying to do from differential geometry is that you had to have the edge placed between two nodes, between the vertices. But further down, where you're now talking about unary edges, it looks like they're only moving one node across. Shouldn't they always move? Okay.
No, this is a very good question. I like that you remind us right now of this. I mean, I did say that it was a cartoon for the actual picture, that we were just trying to do some kind of prototype to see how to sort of test the ideas. But I like that you bring us back to this because we might not want to get super derailed and then realize that when we go back to the edge place picture, we actually can't
get back.
Yeah.
It's like Inception. You go too many dreams deep and then you can't get back.
Yeah. So, you see, I think that the reason why I took the cartoon, and maybe the cartoon is actually an isomorphism in disguise. So, okay, my argument here is we're gonna have multiplicities for all the hyper edges, right? So maybe all the difference here is that you might have unary edges proper in this hypergraph, in which case you would have black dot or vertex place multiplicities, or you might have edge multiplicities for some skeletal edge, in which case you would have red dot or edge place multiplicities, right? So in the picture below, you could imagine that you represent all those multiplicities simply as unary edge counts, right? So the vertices are the actual unary edges, and the edge vertices, this red, the new vertices, you just create as many edges as you had hyper edges on that position, right? And so that turns this graph. So you have this kind of graph where the tangent graph of your original hypergraph, and then you can represent the multiplicities simply as unary edges on all these vertices, both black and red, right? So then a vector field, according to this definition that we gave, which is, remember, an assignment of a directed edge with a tail on each vertex of the graph, but exactly that way, so that there's never two arrows with a tail on the same vertex, right? And that's true for all black and red. Then that means that this picture is faithful, actually. It means that this picture here is faithful. I mean, you still need to maybe make sense of whether things get to a black vertex or a red vertex, and you would only interpret the ones that go to blacks or something, but the picture fundamentally is accurate in this setting. If you're just making the jump that instead of representing hyper edges proper, you're representing unary edges on the edge place of that hyper edge.
Yeah, that's where I thought that you could potentially say that a binary edge, if you go back to that bipartite graph, like a binary edge contains a unary edge, because you can find that type of graph inside that hyper edge graph. It's basically like a node with two lines, and then a ternary edge has a node with three lines, but it contains a node with two lines. So you can
well, but that's an artifact of going first to the edge place construction and forgetting that you have a labeled edge vertex that is created to represent that. So if you forget that you have a bipartite graph, then certainly you can see that ternary edges contain binary edges in that strict sense, right? But that's like saying, a list of 3 elements contains a list of 2 elements.
Yeah,
sure. But that's not what we're doing here. When we do hypergraphs, like we said earlier in the live stream today, we have single bits of information for the exact number of vertices being related, right? So that means that when you have the edge ABC, you don't imply that you also have the edges AB,
Yeah.
BC, AC, right?
Yeah, I mean, it just feels like there's something to look at with regards to that, because the arity like feels like there's a natural successor type construction, but yeah, maybe not.
I don't think so. I mean, I really think that in the sense that makes sense in a very sort of abstract theoretical setting, but in this particular setting where we are taking the initial hypergraph as ground truth, so to speak, like this thing is God given.
Yeah,
we have no idea where this came from. We just take it, and so if you don't have where this came, you don't know where this came from. You don't know anything about the bit of information that relates this vertex and this vertex.
Yeah.
All you know, there's like a quaternary edge. Like you just don't have access to that information at all. So that's why I'm saying I think this is a faithful picture, and that's why I'm bashing my head against this, and I think it's worth to spend an entire live stream just figuring out whether this kind of construction makes sense at all. To try to define something like directional derivative of flows or something like that. Yeah, and perhaps, I don't know, maybe we try to tackle the most characteristic property of derivatives, which is the fact that they satisfy Leibniz rule with respect to multiplication. We get somewhere. Now, I have no idea how I should think about multiplication of multiplicities, to be honest.
What's the difference between addition and multiplication in the first place? Because there's some multiplications that result in, like, multiplied by 1 results in the same amount, right? Whereas at addition, there's nothing you can add together that results in the same total.
Well, you can add 0. Normally, that's
okay, so that's acceptable.
That's that's not usually the difference. The difference is their mutual interaction. So multiplication distributes over addition, and that's how you normally distinguish them. Because as operations, they are the same. They are commutative associative. But the distinction is that, well, they have different neutral elements. So 0 is not the same as 1. That's one difference. And the other very important difference is that multiplication distributes over addition and not the other way around. So that's the two ways in which you strongly characterize that.
Are they both additive? Like, what's the difference between addition and additivity?
Additivity is just a general property that says you behave like addition. So
is multiplication additive?
Well, I mean, technically, yes, because as I said, they are both commutative and associative, so algebraic, and they both have a neutral element. And so in that sense, yes, but multiplication is only, you can only really spot multiplication and distinguish it from addition. Otherwise, you would call it something like a composition or something like that, or commutative composition or something, only when they come along together. So when you have two binary operations, it makes sense to say that one is additive and the other is multiplicative, because one has one identity element, the other has a different identity element, and then when they interact, one distributes over the other. And distributivity is an asymmetric statement. Times distributing over plus is not the same as plus distributed over times, right?
So you could have a hypergraph representing the additions of hypergraphs.
Well, you could do, yes, we could do. I mean, this is more the direction of the sort of higher arity project and all the stuff that I'm doing in the metamathematics kind of direction, where you use hypergraph diagrams as algebraic substrate, right? As diagrammatic substrate. But I don't think that's going to help much here necessarily. I mean, it might be nice to just also throw it at this and have that in mind.
How does multiplication happen in vector fields then? Or is that the wrong analogy?
No, so vector fields are not usually, so you don't, in geometry, you only know how to multiply functions just by definition. To combine vector fields together in a way, you can only combine them either by adding them or by taking their Lie bracket in geometry. So Lie bracket is this sort of commutative operation of flows.
Okay.
Or the lack of commutativity of the flow composition. That's so. But you can multiply vector fields together in general. When there's more structure like a metric or those kinds of things, then you can start to add more operations. But fundamentally, there isn't more than that.
So couldn't we say the same thing for hypergraphs, that fundamentally?
Well, the point is that we do have functions, and we are thinking about functions being these multiplicity counts. So we've very trivially spotted that hypergraph addition is additive. I mean, that's a true statement. That's not a trivial statement. That's a true statement, because multiplicity counts output tuples of numbers, and those have a natural additive structure because you just do component-wise addition. And it so happens that when you do, multiplicity count of A plus B equals multiplicity count of A plus multiplicity count of B. This is a true statement. This is fine. So the problem is that that's not particularly rewritey in scope. It's not. It's just a very sort of like base groundwork construction. And so the question is, what does it mean to multiply two hypergraphs? In other words, can you find a hypergraph construction such that when you take multiplicity count of that construction with A and B, it equals multiplicity count of A times multiplicity count of B? That's a more concrete way of asking the question, right? And perhaps we can think about that for a bit here. So just to repeat for everyone, because maybe I was being too wordy about it. Can the same way that hypergraph addition works additively, can we find a construction, let's call it star, so that multiplicity count of A plus B, multiplicity count of A star B equals multiplicity count of A times multiplicity count of B, where the multiplicity counts are these tuples of numbers. So you just do, and times here is just component-wise multiplication, right? So it's point-wise multiplication. That's I mean, not obvious to me how you would do that. So there's always this nice Wikipedia page of graph product. Wikipedia has a nice. I think I'm sharing my screen. So
yeah, I'm on that page actually. I was since Yuti mentioned, I've been staring at it the whole time.
Yeah. That's the page I had in my mind all this time. So it's good because it's interesting. So number of edges condition for yeah, strong product. Yeah, as you can see, many of these take the product over vertices, right? Like you see here on the left-hand side, the different ones. Sorry, on the right, yeah, on the left-hand side you have the graphs, and let's make it bigger. It's quite clear. Like this more standard products, like the Cartesian tensor, all this strong product, they are a combination of this. They take vertex Cartesian product, so they are graphs defined on pairs of vertices from the vertices that you start with. And what we're looking for is something that will basically do the same as addition. So it will do union of vertices and then some construction on top of.
Is it possible that you could go like the dual hypergraph, do one of these products and then go back? Is that, or is that silly?
That could be actually, that could be a way.
Because
Yeah, I'm just thinking, what can you do with I mean, I guess,
it's hacky, but that's
yeah. I'm trying to
mean-
think of, I'm trying to think of something like, I'm trying to think of something like the, what is this? If you could do a Cartesian
I-
product, so you could
Yeah.
in principle think of just doing a Cartesian product of edge sets, right?
Yeah, and I guess that's equivalent to what I was saying, I think. So you take the Cartesian product of two dual hypergraphs, and then you take the the dual again of that, and get back to where
Yeah.
you were, right? So that
Yeah, I'm not sure. I mean,
There's a Wikipedia article on the Cartesian product of graphs.
yeah, which is the top. It's the top one.
yeah, this is this one. Yeah.
Yeah.
But this is just one example of the ones that they don't do what we want, because we want the vertex sets to be the union of the vertex sets. So we basically, at the level of vertices, we want to be operating like addition of hypergraphs, and none of these constructions seem to be operating like that. Or maybe this one does. The disjunctive product maybe does, because A relate to B and no, it's or. No. Anyway, I don't think the zigzag product wasn't it. I don't think. No. So yeah, I'm just trying to think abstractly. It would be interesting. I mean, this is the funny thing, right? Like, it's kind of an exercise almost. I mean, anyone in the audience has probably has as good a chance at getting this right as any one of us does, I think. But the question is, can you find, and that's an open problem. I mean, we should always, if a live stream should never end without one of two, either a clear progress or clear new definition or clear new result, or a clear new open question that needs to be answered. We should never finish a life science without any of those. So I think this is a very good open problem. I think we have some time, maybe like 10-15 minutes to think about it if you feel like it. But is there a natural hypergraph construction that is multiplicative in this exact sense that we're saying? So that is I mean, multiplicative with respect to edge counts. That is. Because obviously the Cartesian product is multiplicative with respect to edge counts. Well, no, sorry, the tensor product is. So you do some kind of weighted tensor product, and then you get, like 1/2 of this is exactly edge count of 1, edge count of 2, and so you have what you want. But the problem with the tensor product is that it just creates all these new vertices that we don't want. There's basically the Cartesian product over the edges themselves. So yeah, can we think? The thing is, we can do whatever we want with the edges themselves. Like, as long as we don't create new vertices, we can just take those and do any construction with them. Just multiply them. I mean, just I don't know what could be.
Why don't you just multiply the count of the multiplicities in the first term with how many times that thing exists in the second graph that you're multiplying it by. So if you have the hypergraph that you're trying to multiply, if the hypergraph A multiplied by the hypergraph B, and you have like 5 unary edges, and then in the second hypergraph you have 10 unary edges, why don't you just multiply 5 by 10 and then create a new hypergraph that's got 50 unary edges?
No, but but the question is where are those edges? Where do they go? That's the problem. That's exactly the problem.
And just overlap.
Yeah, but that's the definition of the problem. We're trying to kind of operationalize it.
Exactly. That's a good characterization of what we're trying to do. So that's the intuition. Now the question is which edges should be created.
Is it like, so that example you had before where you were adding the graphs, there was some kind of compatibility, like subgraphs of each were sort of compatible, and that's why the edges. I just need to see it again. Yeah. Okay. So
yeah.
And
I wonder if Nick is zoned out, which is very understandable if so. But do you have any ideas?
Yeah, well, that's also I did zone out.
But I
So
mean,
no
like,
idea.
the two basic options is you just multiply them at the spaces where they exist in A, or the other option is where they exist in B. The challenge is that's not associative if you do it that way, right? You need it to be that. It doesn't matter which term comes first, which hypergraph comes first.
Well, the point is that we need, like, the problem that we set ourselves is that you want a construction that counts edges. It's like we know the multiplicativity cannot be built in. You can't multiply anything at the level of the construction with hypergraphs. The construction with hypergraph needs to be something like, you join the edges in this particular way, or create new edges that are like following some kind of rewrite rule that is deterministic or something. Like perform some basic hypergraph operations so that at the end of that process you have a hypergraph with some edge count. Take that edge count and then check that edge count factorizes for the 2 edge counts that you have. That's the challenge. Sorry, Nick, what did you say? I didn't hear you.
Well, nothing in particular.
he said that he did zone out.
Yeah.
Okay. No, this is very understandable. This is a zone out kind of moment.
So what's wrong with that? I mean, why does it matter where you put the edges? Why don't you just put the edges anywhere as long as they don't create new types of edges?
No, because that's not deterministic. That's not constructive. That we can define something like that. Like you need a construction that given hypergraph A, given hypergraph B. I mean, it's on the screen right now. Like given A, given B, A plus B is one hypergraph and not another, right? So I would like to do something that I don't know if we had actually. Did we have I think we had some meaning for this, right, Nick?
What do you mean?
I mean,
Oh, look, it's implemented now.
no.
We should have just tried that. We would have been done in 5 minutes.
No. So, but yeah, the point is,
I guess in answer to James' question, I mean, the question I propose would be, what are the atomic operation? If we're doing some constructive thing, what's our menu of operations that we can legally apply?
yeah.
Some examples of what they are. Presumably some of them are used in this addition examples, and so I guess I'm asking what are those operations, right?
So what's interesting to me is that it might be, and it gets kind of interesting. I mean, I don't know if it works out, but it might be that you want to do some kind of combinatorics, meaning, so, okay, let me give you the simplest example I can think of that I can draw at the risk of crashing the thing. Oops. So imagine that I have a hypergraph that is like this. So I'm gonna return this, okay? And then imagine that I have a hypergraph that is like this. So these are both on 1 and 2, right? So the edge count here is 1, the edge count here is 2. So we know that the edge count of the product should be 2, right? 1 times 2. So why don't we do first? So that's hype 1, and this is hype 2. Why don't we, the construction goes like this. First, take the addition, right? So you have this. And then, so this has too many edges right now, right? Because it has 3, we want 2. So why don't we then say, apply some rewrite rule that takes one edge from one hypergraph, from 1, and one edge from hypergraph 2, and makes some higher arity edge out of the 2. So the simplest way that I'm thinking here is by kind of absorbing lower arity or something like that, right? So the rewrite rule here will be, I mean, this is really tempting the notebook to crash, but I can try to draw the rewrite rule that I mean. So if you have on the one side something that looks like this, right? You just absorb this lower arity edge into a single binary edge, right?
Yeah.
So this could be, for example, the rule that applies here. So when you apply this rule, I don't know, mold rule or something. And so when you just apply it here, I have a function for this. What is it called? I have to evaluate it here. Rules state. Rules and state states. So if I apply mult rule on this thing, okay, that's not the function I want. I want this one. And I say 2. Why? Well, interesting. Anyway,
So you removed it twice. What's the problem? You
no,
applied
no, no,
it
no.
twice.
I was just, yeah. I was just thinking that, yeah. You applied twice, but I was thinking that I was gonna get, because I don't delete the edge, and I can apply it twice. Shouldn't I get 2 edges on the same graph?
Well, you're still preserving the same vertices, so I don't think so. You never introduce any new edge at any point.
Right. Okay, fine. But anyway, this is just sketch. So it works as a sketch, right? So as a sketch, I'm basically saying you now have an interaction between the edges that is based on the adjacency or the incidence structure of these edges. And I mean, in this particular case, this works. I mean, obviously this, I don't think this generalizes well, because if there is no incidence, well, if there is no incidence, actually, oh, that's actually nice. If there is no incidence, then the result should be zero. This is like, if the function evaluates, if some of the functions evaluates to zero somewhere, the product with another function is not zero, there is also zero. This might actually be onto something. Do you, Nick, do you understand more or less where I'm going with this?
No.
Okay, let me make it clear. It's important that someone gets where I'm going with this. Okay. So with this, Richard, do you think you know where I'm going, more or less?
I'm following what you're doing. It's just at the end when you have these two separate rewrites, right, where that unary edge can match on either end of the dumbbell or whatever.
So the idea is, okay, no, this is actually fine, because what I want to say is that, you know, how can I mean, I just wanted to do in one step. Like, how can I apply hypergraph addition over this list?
Oh, you want to fold it, right, or something, right?
Yeah. How? What is a quick way of doing that?
So it's like fold
like that.
Yeah, and then like. Wait, sorry. You're basically trying to reduce a list by total. So it's I think total should do it.
Oh, right. Right. That's true. Yeah. Symbolically.
Yeah, sorry. Yeah.
It's going to do it. Yeah. It's going to do it with total, right?
Yeah. Oops.
No.
That's what I was thinking. So do we get a multiple edge there? Yeah.
That's the thing. Okay. Sorry. That was very simple. My point. Okay. So you might not believe anything I've written down on the notebook, but you would agree that this computes the right multiplicities, right?
By lifting the arities up and then sort of collapsing all the possible rewrites into one final graph by addition.
Yeah.
By hypergraph addition.
So here's the process. I'll just recap the process, and then I will explain why I think this is a viable direction. First, I take the two hypergraphs, right? And as a model, I take one with two unaries and one with one binary. I take the addition, so I consider them together, right? So the incidence structure is now common. It's like put together. This is basically implying that we have information about the common incidence of both, right? The common incidence structure of both. And then what I do is I apply a set of rewrite rules that try to pick up the incidence by creating edges that maybe, and again, I'm not final on what this should look like, but in this particular example, what I'm saying is like, I'm going to absorb lower arity into higher arity. So whenever there is an incident binary with a unary, then the unary gets absorbed on the binary, right? So if there were more, you would get as many instances as there are such incidences. So if I had like two unary edges on one, then I will get two instances of this, right? So you get this idea of, right, of like multiplication, because as many as there are, then you get for one that many. Okay, let me maybe make my point even clearer. How can I easily, well, look at this. Can I do this? I think it's not as simple as that.
Yeah.
Right. So now this should look like this, right?
Mm-hmm.
Let's see if this works. I don't know if this is going to work. So now you would have more instances of those, right? So
Yeah.
there you go.
Oh.
It did work. So the result should be 8. Is that 8? No,
More than 8.
it's more than 8. Let me see. Oh, maybe I'm doing it too many times. Aha. There you go. Is that it?
Yeah.
That's 8.
It's
Right?
8 binary
That's
images, yeah.
Okay. To prove my point, this multiplicativity here. So I don't know if I'm
those-
but
Are those
I-
unary edges? Those unary edges have sort of snuck in this time, though. Is
yeah,
that
I don't know why. That's besides the point, I think.
Mhm.
I think because yeah. Oh yeah, because first time you rewrite and there's still one left or something like but I hope I'm trying to I'm making this point more or less clear. Nick, do you see where I'm going now?
Yeah, I see it now.
Okay.
Yeah.
Okay. So I think there is something going on here, right? Where I like two things about this. I like that we are in implementing the multiplication operation with rewriting. So we are implementing with the super trivial fundamental addition that we already agreed.
The addition is like just bringing your arguments together in a nice way, like taking A and B and putting them into the one
Totally.
machine, and then I like that.
Exactly, Richard. You're exactly right. That's what you think. And then when you have to do some heavy lifting to actually pick up the multiplicity property, that's where you have to get rewriting. But you need to do some kind of rewriting to do that. So anyway, this is my sketch. I'm not convinced this works, but I have no better ideas than this. This seems like a way to
It's
break
nice because
into multiplicativity.
It avoids like a graph theoretic hack, like what we were looking at before, like the products or taking the jewels and all this kind of thing.
Yeah. So let me just for my own records. So I'm just gonna
hit save. That would be the that would be the thing for your own record.
So so I wanted to have this, so I'm gonna copy this one below. And I can do the simple one. Just leave it. Oh, the edges appear.
Because you had a 2 on the end. That was the only difference when you had the 2 at the end of rule state generation function as the last argument.
Oh yeah. That's right. That's fine.
So that should get rid of them, but I don't really know what that argument.
No, but that's applying the rules again and again. Okay. So because you have these, I think they apply more times. But anyway, just to remember that I made a point about this, and yeah, and now you have this one.
So it's maybe like you want to apply the rule until normal form. Always.
Or you might even want to do the one pass trick, where you. I mean, I don't think I have the one pass function here, but you know, this idea that you only output the matches, right? That's what I was trying to That's what I was trying to replicate. Because if you have the one pass, then it's kind of obvious, right? Because remember, the one pass means that you output a hypergraph that is on the same vertices, but it starts off empty, and you only fill it in with all the outputs of rule applications.
Okay.
Right? So given that, imagine that's the case. Okay, let's think that we have that that procedure. So we do these two, we do the addition, and now we consider this rewrite rule, and we do the one pass. The one pass clearly has two matches, right? Unary on 1 or unary on 2. So the output will be just two edges, which will be this, but without the unaries. So the edge count of this thing will be 2, right?
Yep.
Yeah, the one I don't have the one pass function here. I have it somewhere else. I think I can get it very quickly. Maybe we can even finish that off. Maybe in chemoids. Not in chemoids. It's not that one. I think it might be in hypergraphs. Maybe here. Yeah, this is the one pass. But I used it recently. Where did I use this? Okay, I'm gonna copy just in case from here, but I cleaned it up and made sure that it worked with the new backlit. Hypergraph vectors, this flattening, blah, 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 but oh, I think I used it here, maybe? No, I just used it for, okay, so. Vertex coordinates, yeah. Don't need any of that.
No.
One pass. So I think this should do the one pass with the same. So is the rule is a single rule? Yeah. So alt rule, and here I put this one. Yep, there you go.
Nice, 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 nice.
Yeah. So same idea here. So I just can remove this. I mean, come on. Just
Can I ask a higher arity question? Well, once you've
yeah. Give me a sec.
oh,
I kind of want the vertices here, so. I mean, this is kind of stupid, but easy. Yep. Let's pray to the gods. A back practice that I'm doing that. And now I should just copy this.
sometimes you gotta have faith. Sometimes you gotta pray.
No, this should be 8, not 4. Why?
I mean, that's not really sort of functionally equivalent to what you had before, right? Because you're applying the rewrite rule to this. I kind of need to see that line that you got rid of.
Which one?
You deleted it a few minutes ago, but it was like where you had implemented.
Oh, with the total thing.
Yeah.
I'm
just wondering whether it's like
that just applied the rule and gave all the outputs of the rule. The one pass. That's why one pass is not working.
Yeah, that's why I'm saying.
Yeah, because one pass is
functional
actually it's filling out an empty hypergraph. Wait, but that's kind of what we want. And we wait. So it matches twice here, it matches twice there.
That's where you're getting your.
I'm not getting this because it should match twice per. It should match twice per vertex.
Aren't you expecting 4, or am I missing something?
No, I'm expecting 8.
8, because we have.
Because that's the multiplicativity you want, but you wanted to say, okay, unary with binary happens in how many different ways? It happens unary with this binary, and then this unary with this binary, then this unary with this binary, and this unary with this binary.
Which is
So that's 4.
4. Maybe it's okay.
I mean, it's not okay but we might. So it might just be a matter of, okay, so that's binary with. It's binary with unary, but if this is an intermediate step where we put everything into a single hypergraph addition, then there's no way to tell where the edges came from, right? So then we should have a rule. So this should be multi-rule 1, but we should also have a multi-rule 2. I want to say.
So it's a true multi-rule.
Yeah, I mean, what I mean is, I want to have we'll draw. We want something that looks like this. Whenever you find 2, the interaction of the binaries with the binaries. Whenever no. No.
Is it a single binary goes to?
As long as this is going to match for.
Oh, I see.
Yeah. So if you did this, but if you allowed for, I don't know if the pattern matching is going to allow for this. I don't think it will. But I think this is the point. Oops. Shit. Oh, come on. It's already crashing. Okay, whatever. Can I can't. Fine. Well, I don't think I mean, Nick can confirm it. I don't think the pattern matching was going to work. But the idea is that, you know, if I just modify this and say, where is it? Hyper edges. Here, let's say 1, 3. And for some reason,
The styles are no longer applicable to that particular hyperedge.
all right. So I should delete everything, right? That comes after.
Hey guys, I'll have to run unfortunately. I'm still struggling with like the intuition behind the stuff that's happening because I missed like the first half of the like the first I think 15-20 minutes of the live stream. And so I'll try to review the stuff that
Okay. Yeah. But remember that the problem, the open problem here is, can we find a multiplicative
right, yeah.
construction on hypergraphs? That's kind of the thing that we're trying to get to.
Right, yeah. And I think like the categorical operation is not enough because you need something that's more algorithmic in nature. Or
Yeah.
like, yeah, I mean, it's an interesting question and I'll think about that.
Thanks,
Yeah.
UT. Appreciate it.
Great, Udi. Thanks.
Yep.
Cheers.
See you later.
Bye.
Bye. Bye. Thanks.
What's missing here? Just one.
After the first hyper edges, you need a brace.
There you go. Okay, whatever. So this is not going to work, right? Because if I call this, I mean, we might need, what I mean is we might need labels to make this work. But this doesn't. Oh, wait, it does. It does match. Okay, so then, so this is going to be a bit hacky, but okay, maybe I can actually make my point. So we do the one pass first, and then I do a one pass on this thing, right? With the, no, wait. Well, technically I do one pass on this, and then I do plus one pass of, this is mod 1, mod 2 of the same thing. And we're gonna get the extra unaries.
Oh,
But if we do, yes, it's count of,
it's definitely eight. Hash. Oh, this is a percent.
8. That's all I wanted,
Nice.
right?
Very nice. Yeah, that's very nice.
Anyway, it's very hacky, but I hope you guys see what I'm trying to do here, right?
Because you were saying that it's sort of like coming from the two separate graphs, you need to kind of apply.
Yeah. Because the reasoning here is that I don't know if this is the correct approach that we should do first addition, but thematically I kind of like it, because if you think about it, that's kind of like saying that multiplication is iterated addition.
Yeah, but which is the point I was starting with at the beginning when I was talking about hyper operations and
You did. No, I very much remember your point. Yeah.
But this seems a little different. But
it is more than that. Yeah, it's the hypergraph version of that, in my opinion. So I'm not very uncomfortable with the fact that you have to use hypergraph addition.
no.
But then, so right. So this is some kind of square operation.
Yeah.
What's happening here? What you think about it, the square. Okay, interesting. Okay, so this might break down into two simpler problems. So we might, given a hypergraph, right, it has a multiplicity count. If there's a construction that is multiplicative, basically that would be the square of the hypergraph, right?
Take the square root. The function.
Yeah. What I mean is that you just take the square of the what I'm trying to say is that whatever this construction is for two hypergraphs, when you put the same hypergraph twice, you're getting the square as a result. So clearly what I'm doing here is at this stage, I have a single hypergraph. So at this point, I am constructing something that is uniquely determined by this single hypergraph and not the factors. But that's not entirely true, is it? Well, no, it is true, because all this is saying is that there is binary unary interaction and there is binary interaction. But in a sense, that should always be true. The kind of maybe pairwise interactions that you can think of, it, sort of incidence interactions between the edges. I don't know.
What happened to the zero edge, the little vertex that's lonely on its own there? What happened? Did it get sort of pruned or
this?
like-
Oh no, that's just the rewrite rule specification. So so this means that whatever 1, 2, 3 were, the new link is between 1 and 3. So in this
oh, so it's only the addition that actually hooked it back up again, kind of thing.
well, the thing is that the rewrite rule is non-destructive, right? So it just says whatever 1, 2, 3 were, and because the pattern matching is working in that, this is in the rule applications down here, they do 1, 2, 1 or 2, 1, 2, right?
Yeah, yeah.
So that's why you end up with these loops when you rewrite, right? Because the edge that you end up rewriting is 1, 1 or 2, 2.
Can I please just see the one pass writing mult rule 2 on its own, just to
Absolutely. Yeah.
Just
This one, right?
Yeah, just to see it so I can intuitively.
Yeah, for sure.
Right.
Yeah.
Makes sense. And it's
Makes
just the
sense, right?
addition that brings them together into the one graph kind of thing at the end.
Yeah. Yeah. Well, actually, wait. What's happening there? Yeah, it's taking actually it's doing what it's supposed to do, because it takes first this edge and then that edge and combines them on this edge, sorry, on this corner, on the 2 corner, and then takes first the other edge and then the other, combines them on this vertex, and then the same thing for this vertex, right?
Yeah.
Because the rule application, the pattern matching happens in 2 possible
2 ways.
orientations.
Yeah.
Because there's this symmetry. So, which I think, well, maybe that's wrong. That might be wrong. Anyway, it's been too long. I don't think we should. I mean, I think this is a good enough trail to chase.
I was wondering what happens if you have that hype 1 plus hype 2. If at some point down the line there's some other operation for which there isn't a kind of natural like higher arity equivalent, like obviously with multiplication you can just, well, the question really is, will there ever be a time where some construction like this has hype 1 plus hype 2 plus hype 3 and
Yeah.
so above there where you're bringing your arguments together in one kind of unified graph with hype 1 plus hype 2, it kind of feels like you could just do that with more like with hype 3, hype 4, and then you would have these operations which are kind of higher arity in a sense, like doing things on sort of more than 2 arguments.
Yeah. No, you can definitely do with more arguments. I don't think that's going to be a problem.
Yeah, it's just, like the binary multiplication, you can just do it like A times B, that times C, or the other way, the A times brackets B times C. But it's like doing it this way, you're kind of doing it more as a 3 arity operation, or whatever you like, kind of thing.
Yeah.
It seems like a nice framework for building kind of any operation you like on any number of arguments.
What?
It's because the last thing you did was the example I asked you to run, I think.
Oh yeah. So now I should do it. So, so if I just copy this, I just wanted to, as a conclusion, do another example to illustrate why I think this might make sense. Because it's not only that we get multiplicity in the obvious sense, but we also get this kind of thing where, well, it doesn't really matter. So if I have, so delete that. Now delete these. Now add new one. That's it, right? So I have something like this that has no incidence with hype 1, right? So this is going to look like, oh no. Wait. And this. Oh yeah, there you go, right?
Okay.
So it doesn't matter what, so one pass of rule 1. I mean, I guess I can just, well, this is the output. So just place it out here, place it out there. If everything is as I expect, this should be the empty hypergraph. Oh, what? Oh, no. Yeah, because, right. So that's where this might be too reductive, too simplistic. That's why I always thought this was kind of a hack to do. So the point is, okay, let me just do one at a time. So the point is that the output of this is the empty hypergraph, right? So, which is exactly what you expect in terms of multiplication of functions. Like your functions are going to live on are the multiplicity counts of your edges. So if the edges don't have an incidence, they are going to multiply to 0. So you are going to get 0 out of because you know the multiplicity function in here is non-zero between 1 and 2. The multiplicity function here is only non-zero in 3 and others or whatever, right? But anything involving 1 and 2 is 0, meaning there is no edges that populate 1 and 2. So this process, even by doing this, when you look at the rewrite rules, like the ones, you know, in this case, there's only binary and coming from one and binary coming from the other, and unary coming from the other. So maybe, you know, you say you only have unary and binary interaction in this particular case, because you're assuming that your inputs are simple, your arguments are simple to begin with. Then the output should be empty and the edge count should be 0, right? That's multiplicative as well. That it's not only I mean, yeah, what I'm trying to say here is a little bit beyond just the. So remember, we are trying to recover multiplication of functions. This is not to say that edge count. I mean, edge count as a whole is a placeholder, right?
Yeah.
Because edge count is just putting everything into one single bucket. It's like integrating a function over a manifold, right?
Yeah.
It's like adding all the values of the function over.
But you want to be doing it at the individual sort of points of the function, all the x's of it.
Exactly, right? You want a new. The point is that you want a new hypergraph. This is the whole point, right? The whole point is that you want one new hypergraph to look at. So this is a new hypergraph to look at, right? And it's basically telling you, oh, your product happened to have no overlap. Your hypergraphs happen to not talk to each other. Therefore, their product is the empty hypergraph, which is exactly what happens with functions. You know, if functions have, you know, one function is 0 in some area and another function is 0 in another area, and those two areas don't overlap.
Yeah, like the Hadamard of vector 1, 0 with 0, 1.
Exactly. Yeah, exactly. Very simple. Okay, anyway, I think that's something. I think we have something to go on. But yeah, it's quite tricky. But anyway, final thoughts. This went way too long. I apologize, but I really wanted to have something.
Don't apologize.
Nice.
It's nice to see the process, and I
Yeah.
hope I didn't impede it or anything. Just trying to get up to speed of what you're doing.
Oh no, you were super helpful. No. By any means. I mean, that was super helpful actually.
I in a very hacky way for my winter school thing did something like slightly different, but it's a complete cheat because it was done with combinators, and instead of looking at multiplicity, it was like I picked like the Hausdorff dimension because that gave me, for each vertex, it gave me some quantity that I could measure, right? And then and the whole thing was just like I took a very basic idea of like, say you have like a Taylor expansion for some thing like sine.
Yeah.
Then you could have a system that down particular directions would represent sort of progressive compositions of that function with itself, kind of thing. And I on the output, it sort of very crudely approximated like a damped harmonic oscillator or something funny came out of it, and I was like, but it was but it's cheating because at the beginning it's all done with combinator, so I can just write in like combinator language. But I suppose those are going to be just DAGs at the end of the day. There's no cycles. There's no so you're kind of just rewriting expressions. You're just rewriting terms, and it's a little easier to deal with.
Yeah.
But it's like similar in nature, but just not as simple and not as principled, not as algebraic or whatever. So but that was coming from my naive perspective at that point. But
Sure.
yeah, this is interesting.
Well, thanks very much, Richard. Nick, any final thoughts? Do you see a path ahead?
I'm trying to.
Okay, but you're getting my thoughts more or less, right? You see my intuition more or less where it's going.
A little bit, yes.
Yeah. Okay, great.
But
No, we
need
can
to
do
flesh it
some.
out a little bit more, yeah.
Yeah. But at least the problem seems to be more or less well defined, right? That's what we're trying to do.
Yeah.
Okay. Yeah, we'll do some one-on-one next week. We can come back to this.
It would be nice to see eventually like the general case or some way of, because you have to prescribe these rules, right? So depending on the arities
Yeah.
of the hypergraphs.
Yeah, that's the real problem. That's the real solution to the problem, right?
Yeah.
Like, given two arbitrary hypergraphs, which rules do you apply so that you
lift
rewrite? And
yeah.
I am thinking of I don't think that might be that complicated. It might be that is some very simple sort of incidence pattern kind of rewriting, which, it might be even something that is fully conservative, like that is just the identity rewrite rule, but because you're applying it to the sum, that might do the trick. Maybe not. I don't know. But the point is, I think that the sketch is out there, and we can keep discussing because it's been long enough.
Cool.
But yeah, thanks so much, by the way. Sorry that it was mostly just a stream of thought and just trying to bash our heads against this particular question about how to define a function multiplication. But I think that's exactly the spirit of infrageometry. It's just like burning ourselves to define the thing that takes one single character in the first line of definitions in a maths book, right?
But once you have that, you can then build these directional derivative properties or
Totally. All right, James, want to close?
Good.
Any thoughts?
Yeah, so thanks so much for that. That actually felt quite productive in terms of exploratory, branches. We definitely covered a lot of ground there. So, and I appreciate everyone for jumping on and contributing. And I see the chat also. It's we got some good input from the chat, but it's definitely, it feels like at some point it becomes contemplative. Like if there's sort of like these times when you can make a lot of progress, and there's other times you have to slow down and really think about what to do. But it's nice to see that in real time. And once again, that's the value of having a live science session, is you get to experience that. It's not just a presentation. It's like this is the struggle of trying to do these things. So awesome. Well done.
Yes. I think, thanks very much, James, and thanks very much, Nick, Richard, and Uti, who was here earlier. I think the viewers get the benefit to see both ends of the spectrum. Like in the morning, it was just presenting the very clear ideas of things that have been well, understood by large chunks of the mathematical community and CS community. And you got to the very end of the day here where we bump our heads against the walls of understanding, like these things we don't understand. We need something, we are hacking our way. And I think today we made a pretty representative example of what research is like. I mean, all the way from clarity and basic definitions to things that are frontier and weird, and we are confused, and so yeah, thanks very much everyone for this. This is why I signed up for the Wolfram Institute. So I'm glad to be here.
Great. All right. All the best. See you guys.